So reminders, we have an exam on Friday. We have an assignment due tomorrow. I'll have office hours available after this class to go over anything assignment related, but does anybody have any clarification questions on the study guide or would like some help figuring out how to study for the exam?
Good, all written.
I haven't fully written it. My plan is to write it this afternoon.
Oh, I mean, like paper.
Oh, paper, yeah, everything should be paper and pencil, but nothing.
And multiple choice.
Probably not. I haven't fully decided everything, but my usual style is either writing code or some kind of short answer that explains your thought process. And then anytime I do that, there is always full partial credit available with the entire spectrum of the grade scale available for partial credit.
We graded on the syntax then?
Yeah, I'm not gonna require 100% syntax, 100% correct syntax for any written code. I would more so look for the block and kind of ideas. Although if you write something that looks more like pseudocode than Java, or something that looks more like some other language than Java, then I might start taking some points off. But if you forget a semicolon somewhere or misspell the name of a function that we both know that if you were writing this in an IDE, you would have an auto fix available for you, then that's not a huge deal from my perspective. We're also looking for the big picture ideas than perfection.
How many questions did you put on?
That's a good question. The questions will vary in length and in how much time that I think it will take. So I will do my best to not crunch people up against the end of the class period. This is why I have more exams in the class, so that I can try to reasonably tackle the amount of materials. We haven't covered that much. And that way I'm not feeling like I need to write so many questions that it's gonna take people 75 minutes, but you only have 50 minutes. Goal is so that you can fully express yourself and make sure that you do the best that you can on each of the questions without feeling a ton of time pressure. That's the goal. I can't guarantee it, but if that's the case, then I'll obviously curb exams or do something about it if the result is not something that I think is good for the health of the class as a whole. Other questions before we get started? I will continue to ask this tomorrow as well. Yeah, those of you who are remote will be taking the exam on Friday. I need to figure out exactly what to do, who to send things to. But I can add that to my to-do list to do today, and then I can get in touch with people who are taking it remotely to make sure that you have access to it. Thanks for the question. Then what else? Thursday's class will be the review period, so please do your best to come prepared with 4 or 5 questions. These can just be topics of something like, I'd like additional practice on this. I feel a little bit less sure of that topic. The sooner you let me know if it's a generic, a very broad question like that, I can come prepared with practice problems or something else of the sort. Otherwise, I'll have to invent it on the fly. Sometimes I'm okay at that. Sometimes I will get a little baffled and try to have to find something on the fly. But we'll make it the best that we can. So last time we talked about bubble sort. We got as far as basically being ready to implement bubble sort. We're gonna spend some time working on it, but let's go ahead and actually just start implementing, because I think that will be what is most useful. So just like I did before, I am going to attempt to dock this tiny window on the right. With our pseudocode, and we will dock this on. Let's. Little bit of a small sight to see, especially if you're remote with our lovely standard definition. But I think we can make it work. Gonna make a new sort. Eventually show up. Maybe. Maybe we get to spend the next 2 minutes while Eclipse restarts. Guess we get to do that. While that happens, does anybody have any questions about bubble sort? Or maybe we can even start with talking about the complexity of bubble sort while this starts up. So bubble sort, if we think about the example that I did on the board, what is the worst case complexity of bubble sort? What does the list look like and how much work does it have to do?
They're like linear. Just like that, dollar sort.
If it's already sorted, we would verify and just go through in the best case. Sure,
Oh, just say worst case.
I didn't say worst
Oh,
case,
sorry.
but no, that is a very good best case analysis. Yeah, it's still quadratic, just like every other sort that we've seen, because in the worst case, the bubbling that we do doesn't put anything in order except the very last element, and then we have to continue to think about that. Reset that, re-zoom in. And now it's back to telling me that the project's not compiling. We'll figure that out. So worst case is quadratic, best case is linear, just like insertion sort, but very unlike selection sort, but usually we don't care too much about the best case anyway. So we're going to return nothing as before. We're going to call this bubble sort. It's going to take an array and we will have some main to call it. So we can go grab our main from any of the others because it's not really going to change except for the call that we use. So I will just copy that, override our main with that main and call bubble sort rather than selection sort. Great. Right now, this does nothing. We want to make sure that it adheres to this pseudocode that we have down here. That again, I apologize, it's not particularly legible remotely. So we want to set, according to this, we need to know the length. But how frequently are we using this length of the list? It looks like we use it once in the for loop. So I don't know if we really want to store that off. It doesn't seem like it's particularly necessary. So repeat until not swapped is the first loop that we see. So we don't know how many times we are going to be doing this. So that sounds like a while loop. So to be able to check until not swapped, it actually sounds more like a do while loop, right? We can define swapped within the loop. Otherwise, if we do this as a traditional while loop, then we end up defining it. And then immediately needing to, the very first thing says we need to set it to false again, because when we loop around, we need to make sure we set it to false. So we get this really ugly looking pair of lines where we set it to false and then we set it to false again the first time around. that can kind of tell us that we would rather use a do while loop than a while loop here. Again, I will leave this as it is for the moment, and we can take a look at the end of this, what does it look like to replace this while loop with a do while. So this just looks gross for the moment. For I equals 1 to n, which is the length of our list, minus 1 inclusive do. So we're going to write for from I equals 1 to n minus 1. Why are we saying from 1 and not 0? Yeah, because we're going to end up checking the next one. We say if a of I minus 1, so if we set this at 0, then we're going to be checking the one before 0, which is going to be out of bounds. And it says n minus 1 inclusive, which is straight up less than the list dot length. Got this. Windows machines. All right, now we're starting to see that nested loop structure that we expect out of quadratic running time algorithms. If we said that the worst case was going to be quadratic and we only ended up writing one loop, that would be a little bit strange. So now we need to write an if statement that says if they're out of order, then we want to swap them and remember that we swapped something. So we want to look at the value of the current index minus 1 compared to the current index of I. So we're going to look at if list of I minus 1 is greater than list of I, that would tell us that they're out of order. Then we want to swap them. So we had a way to swap them before. Anyone want to write this swap for me? What are the 3 lines if we want to use a temporary variable to swap? What is it? List of I minus 1, and what is it? List of I? Yeah?
I think. Well, what I did was I just used 10. In 10 equals array of I minus 1. And then I said, array I minus 1 to, I, or array I.
Yeah.
And then I did array I.
That'll do it. If we're gonna do this a bunch of times, maybe we define a swap method. And that way we can just pass in a first and a second, and then we just have to identify a swap. We could even pull that out of bubble sort and insertion sort and selection sort whenever we have an associated swap. We would want to call the same swapping code so that we're not writing the same thing over and over and over again. That would just be an optimization that we could make. So this will swap, and then the last thing it says is we want to set swapped to true. The idea is we're eventually going to go through this entire loop and never make a change. When we don't make a change, we know the list is sorted and we can fall out of our while. What do we think? I think this maps to everything that our pseudocode is telling us for bubble sort. You want to try to test it? Of course, even though I just got something working, so if you ever see something like this, it's always an issue with the build path. So you go to the build path, you go to the configure of the build path, and this module path should be in the class path. So you add to the class path a library, JRE system library, Workspace default, that is fine. Apply and close. It runs. That didn't seem to work. Why not?
We're gonna return the list. Oh, wait, no.
If it passes it in by reference. So we should just be able to get it back.
It's probably the Boolean statement.
What do people see? Yeah,
Shouldn't it be while swap is true, because. Doesn't it like stop when swap equals false?
yeah. So until not swapped means that not swapped is going to be. Yeah, so we don't want to, we'll set it to true here so that it. Is true the first time around. And we want to say while swapped, well, we do a swap. We'll start out saying we haven't done a swap and we expect that sometime through this loop swap is going to become true. When it becomes true, then we loop around and know we made a change, we should continue. And eventually we will not make a change, and that's what's going to have us fall out of the loop. So if we test this. Now it works.
Did you say that again? Why it didn't work when you set it to false and then false again?
So we basically said that while not swapped says that we expect that this is going to stay false in order to continue to loop. So if we make any change, any swap, it's going to set it to true. When we come back around, it will be true. So we fall out of the while loop on the very first pass. We make a single swap, which is why we saw the first and second values swapped, and that was it. Because then it fell out of the while loop. So now this is going to make much more sense. It works. So sometimes when you see pseudocode in a do while form, you'll have to think about how does that map to the while loop form. Very good eyes. Anyone have any questions about this implementation? Does anyone see anything that is suboptimal about this implementation? Is it doing any unnecessary work? Or is it inefficient? It is certainly inefficient. It's doing something that we can improve. Talked about the complexity. What do we know after the very first pass? Yeah, let's start here.
Well, I was just gonna say that like on some of the other source we wrote, I think. Aren't you just moving values like once, like you find that min and then you move it all the way over, go bubble, you're like probably moving the same values over and over again.
Okay, it's very similar to that. At the end of the very first pass, we know that we have the largest value in the last spot. Is our code ever comparing that last spot again? It is, but it shouldn't be. That's exactly right. We know at the end of our first pass through everything, the largest value is in the last slot. But every future pass, we're comparing what is in slot length -1 to what is in slot length. Even though we know that's never going to need to be swapped again. After the second pass, we know the second largest value is in the second to last slot. We never need to compare that again, because we know it's in the appropriate place, and yet every future pass through this, we're gonna be comparing that second to last spot to the last spot. After the third pass, we know the third largest value is the third largest position, third last position. So how much more complicated do we think the code is to handle it? Is it worth our time and effort? Question one that I have for you, does fixing it change any of the best case, worst case, or average case orders of bubble sort? What behavior change could we expect? Does it change the order? It does not. It's the right answer. The worst case is still gonna stay quadratic, the average case is still gonna stay quadratic, but it ends up chopping off about half the work. By the time you've sorted everything, you'll save yourself about half the work. And sometimes now it's worth doing or not worth doing, depending on how expensive we anticipate it being, how much time is it gonna take to implement. So let's take a look. Here's our old pseudocode, just copied and pasted from earlier. Here is the pseudocode of the code where we can handle that. Is it more complicated? Not really. So this tells us maybe it's something that we should be thinking about. If it's not going to make the code much more complicated and it's going to save us half our running time, it's worth doing. So let's see if we can copy our old bubble sort and make the associated change into the new bubble sort to take advantage of it. First of all, what are the differences? What happened between the old pseudocode and the new pseudocode to be able to handle this, not swapping the stuff that we already know is in place?
7, 0, so false statement.
Yeah, we no longer have a Boolean, did we swap or did we not? Instead, we're keeping track of a position that's going to be moving back through the array of everywhere we know has already been sorted. By analyzing bubble sort, we've come to the conclusion logically that the largest element will be in the last position after the first iteration, and likewise. So instead of storing whether we're doing any swapping at all, let's store the position in the array where we know stuff before that might not be sorted, but stuff after that is certainly sorted. And that's what this new n is doing in this pseudocode for an optimized bubble sort. So we're going to be bringing that position in the array backwards and backwards and backwards until we get to the beginning of the array. When we're at the beginning of the array, there's nothing before it that could be unsorted, and everything after it we know is sorted. So I'm going to bring up this pseudocode. Once my computer remembers how to work. And let's just copy this file. And paste it. New name is going to be optimized bubble sort. And now we can just go through and make the associated changes from what we see. So we still have this same repeat until n is less than or equal to 1. N starts out being the length of the list. So we are going to say int n equals list dot length, while n is greater than 1, because if we want to say until n is less than or equal to 1, that tells us that we want to continue working while it is the Boolean opposite of that. The opposite of less than or equal to 1 is greater than 1. So while it is greater than 1, I'll follow this exact. I don't love this concept of new n. That seems like a terrible name. We'll run with it for now. For I is 1 to n minus 1 inclusive, we already did that. If list of I minus 1 is greater than list of I, then swap. And if end 4, so this last line is going to go and be replaced by something after the internal for loop between the for and the while that says that n gets new. And inside of the if, we also said un gets I whenever we make a swap. So we're going to be updating it to the last swap that we do. We know the last swap that we did, everything after that is already in place. So optimized bubble sort will now hopefully run and keep things sorted, which it does. But this should also be about twice as fast as the old code that we wrote. If within 5 minutes, you can write an algorithm that saves half the time, it's worth it. If it's going to take you an entire day and it doesn't change the actual order, maybe it's not worth it. Questions on bubble sort, optimized bubble sort, how either of those work? Reading from pseudocode, implementing pseudocode. Yeah,
This one kind of random, but do you think you can go over the complexity of it, like how we go over the examples?
yeah. So for this, how do I want to do this? That is a great idea. Thinking about how much work is saved between the two algorithms. So let's come up with an example array, and we'll just think of the number of swaps that we had to do between optimized and non-optimized bubble sort. So we have some numbers that are out of order. Shout out to numbers that are out of order.
Well.
Oh boy. I feel like we could turn this into a psychology class and just talk about that for the rest of the quarter if we wanted to as well. So let's start with the number of swaps that are happening here on the first pass for regular bubble sort and optimized bubble sort. So I'm just gonna kind of turn this into a table that says iteration 1, 2, 3, 4, and 5. So it's gonna be the same the first time around. We're gonna swap the 12 and the 5. We did 1. We're gonna swap the 12 and the 3. We're gonna swap the 12 and the 2. And we're gonna look at the 12 and the 17. So each of those would do all of those considerations. We looked at and considered swapping each one. Even if we didn't actually do the swap, we looked at them each. So there were 4 things consistently through both. But we're going to start seeing that the optimized bubble sort, now we know that this is the largest element in the list. So there's no reason to compare this to this in the second pass if we're using optimized bubble sort. So we compare the 5 and the 3 and we swap them. We compare the 5 and the 2 and swap them. We compare the 5 and the 12, Those are already in order. So optimized bubble sort is done at this point, but regular bubble sort is still gonna look and verify that the 12 is less than the 17, which it is. So for the next one, we know that this is also in order. So optimized bubble sort does not need to compare 5 to 12 or 12 to 17. Because we know this is the second largest element, we're never gonna need to swap this. And this is the largest element, we're never gonna need to swap this again. So we compare the 3 to the 2, swap them. We compare the 3 to the 5. We don't need to compare the 5 to the 12 anymore, but bubble sort will continue doing this. In fact, it's always going to do 4 operations, n-1 operations, where the n is the size of the list. But you can start seeing that optimized bubble sort is starting to move downwards. So when I said it does about half the work, what we're looking at here is 4 times, or 4 plus 4 plus 4 plus 4 plus 4. We're gonna be doing n times n-1 amount of work, right? We have n, the size of the list, that's the number of times we're gonna be comparing. And we have n-1, the number of operations to do each time around. And we also know that 1 plus 2 plus 3 plus 4. It's going to be n-1 times n over 2. The only difference between these two expressions is just the constant 1/2. They're the same order. If this were to scale from a size 5 array to a size 1 million array, then it's going to explode the number of work, the amount of work to do, but the difference between them is still going to be half. So that's why I said it was about half as much work. It's exactly half as much. And this entire idea would scale too. So if we had 1 billion, we would have 1,999,999. And then we would be starting at 999,999 and counting down to 0. Which would still turn out to be half as much work. Questions about that? Does that make sense? How we're analyzing the amount of work that we're doing with between the two algorithms? Anyone need anything else on the board? Can I erase it? Where are the rules? An eraser that I'm not seeing, I'm sure. Right in front of my face. Amazing. It's amazing how bland you can be, sure. Me. Okay, so that's basically it for the basic sorts, pun intended. We will see lots of other ways to sort. These are the most intuitive sorts. They're the easiest to write, but they're also the hardest from the computer's perspective. And we'll find this a lot in computer science as you take the rest of this course, additional courses. There seems to be a pretty inverse relationship between how easy it is for you and how easy it is for the computer. If you're having an easy time writing it, the computer is going to hate you and do a lot of work. If a lot of the work is on you, the programmer, then you're going through the optimizations to make sure that it's easier for the computer. So harder work for you will scale better. We'll come back to this as we get more and more tools for figuring out new ways to sort that are more efficient than this from the computer's perspective. But before we do that, we're going to make a big change and talk about recursion for about the next week. So this is also not going to be on the exam that is on Friday, but it will be on the following exam. I need to start talking about it very soon because it's a topic that is very difficult for novice programmers. It's difficult to wrap your mind around the first time you see it, and for a good while after that, it has a bit of a reputation as being a difficult concept. And it's also going to be on the 8th, that is coming up in just a few weeks. So I want to make sure that we have plenty of time to do this justice, to answer all of your questions about it, and to get copious amounts of practice with it, so that you can do the best you can with it, the 8th. So let's start with some fun motivation. All right. Whatever to you personally is the single most exciting thing in the history of ever, you're in line for that. You are very excited to be in line for the most exciting thing in the history of ever. So things that you know while you were in this line. It is long. In fact, it is so long that you have no idea where it even starts. If this were to be some kind of concert, let's say, you just see people in line for a while. You don't know where the concert's actually going to be. You just know that this line eventually leads to this concert. You want to know how long the line is. There's just one major constraint. If you leave the line, you will lose your place in the line, which is not good. So you need to find some way to figure out how many people are in front of you without leaving the line, when you can't see the first person in line. How are you going to do it? The options that you have: you can speak to the person directly in front of you in line. You can speak to the person directly behind you in line, and that is it. You cannot make any kind of global announcement. You don't have access to any kind of social media or the internet to try to look up anything. You have to use just the people in line, and you can only communicate with the person in front of you and the person behind you. And that works for every person in line. Any person in line can communicate with the person in front of them or the person behind them. How do you figure out how many people are in line? Yeah?
You tell the person in front of you that their like count is 1, and then they tell the next person, but then every time that happens, they tell the person behind them, and then the person behind them tells, then it gets back to you eventually.
Yeah, that's kind of the idea we're gonna start thinking about is, you could ask the person in front of you, how many people are in front of you?
You don't know.
And they don't know. Is there anybody in line who knows how many people are in front of them? The first person in line knows how many people are in front of them, right? They know there are 0 people in front of them.
It's like if you said to the first person in front of you in line, like, ask the first person how many people are in front of them, and then pass that message along.
Yeah,
And then eventually it'll reach the first person and go and speak up, and someone will return 0. And then that will cycle back through the line where each person says, oh, there's 1 person in front of me, there's 2, 3, 4.
exactly.
And then it'll reach you.
Eventually it comes back to you and you know how many people were in front of you. You've created this very long game of telephone where on the way down, there's no information being passed along, except the question, how many people are in front of you? 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 All the way to the front of the line until the person in front says, there are 0 people in front of you. The person behind them says, well, if there are 0 people in front of the person in front of me, there is 1 person in front of me. They turn around and communicate, there's 1 person in front of me to the person behind them. From that person's perspective, they know there is 1 person in front of the person in front of them, so there must be 2 people in front of them. This message continues backwards where you add 1 for every person until eventually it reaches you, whatever that value happens to be. And this procedure will work regardless of the number of people who are in front of you. If there are 0 people in front of you, this procedure will work. If there are 10,000 people in front of you, this procedure will still work. So here is the English logic for that. You ask the person in front of you, how many people are in front of you? If you don't know, ask the person in front of you. Eventually, we find someone who knows the answer to this question. And if they know the answer to the question, the person behind them knows the answer to the question. And so it goes backwards all the way back to you until you have an answer. So to be able to solve this in general, we just need to have what we're going to call a base case, which is the person in the front of the line who is able to actually answer the question. They're the only person in the entire line who can answer the question. But this logic doesn't work if nobody can answer the question. We need at least one person to be able to answer the question, even if that person is not you. But we also can see that there is something in common between what is happening. The entire process of this is kind of like a mathematical expression where your answer is somebody else's answer plus one. And their answer is somebody else's answer plus one. And you can kind of start to see this entire thing collapsing on itself like a fractal. Where this entire problem is phrased in terms of a problem that's identical to it, but smaller. And that problem is phrased very similarly to it. It's exactly the same problem, but slightly smaller. And this starts to get smaller and smaller and smaller until at the very middle of this, we have a 0. So if you were to just look at this as a mathematical expression, we can't solve it by just looking at it once, but we can solve this very middle section. And then that allows us to solve this problem with some logic, which allows us to solve this problem with some logic. And so it starts to work. You start to strip away the complexity of the expression until you have something you can solve. And then you apply some logic to be able to solve a slightly larger problem, a slightly larger problem, a slightly larger problem, until you can solve this gigantic problem that you couldn't solve at the beginning. Does that concept make sense? All right. So the way that we do this in programming is to write a method that calls itself. If we see this as a visual problem where a line of an arbitrary number of people is exactly the same as 1 plus a line of 1 fewer people, we end up solving the same problem over and over and over and over again, which means we don't want to write multiple methods for this. We actually only need a single method's worth of logic to solve the entire problem. But we're going to be in the process of solving this for a problem of size 10,000. We're going to be calling the exact same logic on a problem of size 9,999. Solve that, we're going to have to call the exact same logic with size 9,998, 7, 6, 5, all the way down until we have some problem that we know the answer to off the top of our heads. So 2 components we need to be aware of. The base case is a problem that is so simple, we know the answer without needing additional logic. So in the line example, this was how many people are in front of you when you're at the front of the line. We don't need additional logic to know that the answer is there are 0 people in front of me. The other part of it is the recursive case that says we need to phrase the question in terms of itself, where itself is a smaller version of that same problem, or a simpler version of that same problem. So this is when you ask the person in front of you, how many people are in front of you? It's exactly the same question that you are trying to answer. It's just a slightly smaller problem for them than it is for you, because they are 1 person ahead of you. If you chain this together and say, hey, if you don't know how many people are in front of you, ask the person in front of you, you will eventually reach that base case. Unless we have some kind of circular line, in which case eventually you'll get a tap on the shoulder asking how many people are in front of you, and this process never ends. So the recursive case also needs to handle what happens once an answer is returned to us. If someone says, there are 14 people, the person in front of you says, there are 14 people in front of me. What do you turn and tell the person behind you? There's logic where to go from what you heard from the person in front of you to what you need to communicate to the person behind you. You need to add one to it. Because you are a person who is in front of the person behind you, but you are not a person in front of yourself. So you need to account for that in the communication that you give to the person behind you. Questions on any of this logic? It's kind of terminology for it. It's very repetitive. And the person in front of you, in front of them, in front of, can get kind of confusing. But does the overall idea make sense? So we now have the logic for identifying what happens if we're the first person in line and what happens if we are not the first person in line. That creates the base case and the recursive case. We now have logic for both of those situations. If we combine these two pieces of logic, if we are in the base case, then return the answer to the base case. Else, we're in the recursive case. Handle the associated logic to figure out how do I phrase this problem in terms of a smaller identical problem. And then when the smaller identical problem returns an answer to me, what do I need to do to figure out how to return an answer? We have our two different cases. We have a full solution to the problem because we've identified every possible case. So what could this look like? What would a function look like for this? Let's say you have access to functions that look like person in front takes a person object. It will return true whether there is a person in front of you or not a person in front of you. You have access to get person in front that returns the person object of the person who is in front of you. Each person object has an ask method where you can ask them the number of people in front of them, and it would return an integer that is the, sorry, you phrase the question to them and it allows you to communicate with them. It doesn't return an answer. So what you need to implement is number of people in front of a particular person object. So now you need to fill in the rest of this with the associated calls in order to be able to figure out the number of people in front of this person P. This is what we are going to start tomorrow's class off with because we are out of time. So we've set it up. First thing tomorrow, we're gonna write this and figure out how can we actually express this recursively, solve this problem. So I'll see you tomorrow for that. I have office hours starting in my office right now for any homework or exam related questions.